Hi, today I will show you how we can assemble a quantum processor from CircuitQED quantum hardware. I will focus on the approach to fault-tolerant quantum computing named Surface Code, which we pursue within QTech. Surface Code calls for a two-dimensional square lattice of qubits with only nearest neighbor interactions. In addition, these qubits must be individually addressable both for single qubit gating and for measurement. Currently, we are testing Surface Code chips with 7, 17, and 49 qubits. We call these Surface 7, 17, and 49. We assemble all of these using a common approach that we believe scales to larger surfaces. I will now describe this approach using the specific example of Surface 17. First, we lay out the square lattice of qubits. Let me symbolize the qubits by circles. Please disregard their assigned color for now. To perform two-qubit conditional phase gates between nearest neighbors, as presented by Adrian, we add, first, a coupling bus resonator to interconnect them, and second, a dedicated flux bias control line to each qubit. To perform single-qubit gates, we follow the approach introduced by Brian, adding a dedicated microwave drive line to each qubit. Finally, in order to measure each qubit individually, we add dedicated readout resonators. These readout resonators are coupled to diagonally running feed lines and probed independently using frequency division multiplexing, as described by Niels. You may have already noticed the crossing of transmission lines on the chip, which is not possible in a truly planar structure. For this, we make use of the third dimension in the form of air bridge crossovers. Cool stuff, isn't it? Beautiful. So let's look at the totals for Surface 17. 17 qubits, 24 buses, 17 readout resonators, 17 flux lines, 17 microwave drive lines, and 3 feed lines. The grand total of ports connecting the quantum chip to the outside world is 40. We call these ports vertical I/O ports because they connect to the outside world not via the edges of the planar chip as traditionally done, but vertically. In one approach, which we pursue together with Intel, the quantum chip is flipped and the ports connect directly to a multi-layer printed circuit board using a ball grid array. Achieving reliable vertical interconnect has been a key pursuit in our field over the last few years. Now, let's go back to the colored circles representing our transmon qubits. Except on the edges, qubits couple to 7 objects, 4 buses, 1 readout resonator, 1 flux line, and 1 microwave line. These interconnectivity requirements give our transmons a characteristic shape and nickname, Starmon. The colors we assign to the circles denote the qubit operating frequency, at which single qubit gates are performed. In total, 4 frequencies suffice to control a surface code of any size. This affords us significant savings in the microwave frequency control electronics, which unfortunately I don't have time to discuss here. But with regards to the quantum hardware, this repetition of qubit frequencies allows us critically to define an 8-qubit unit cell. By exactly replicating this 8-qubit unit cell and performing the necessary truncation at the boundaries, we can build a surface code of arbitrary size. In fact, we put together Surface 49 test chips in this very way, literally copy-pasting and truncating. We believe this approach will scale to even larger surface code, such as Surface 97. I leave you with the CAD drawing of such a future chip.